Welcome students to the 49th lecture on particle physics. And today we are going to talk about the selection rules in particle physics, particularly dealing with weak interaction processes. See, we had the selection rule when we talked about the different processes and we assigned isotopic spin and third component of isotopic spin, and then took many examples where we showed that the processes where I and I3 both of them are conserved, they are strong interaction processes. Where you have the process where isotopic spin is not conserved, I3 is conserved, then that is an electromagnetic interaction process. And then where the cases where both I and I3 are not conserved, they are weak interaction processes. But here we are going to talk about the processes which are allowed by exact conservation laws, the processes which are weak interaction processes, which should be observed keeping the basic points in mind that they are obeying all these 7 exact conservation laws. Remember, energy conservation, linear momentum conservation, angular momentum conservation, charge conservation, lepton number conservation, baryon number conservation, and CPT. These are the 7 conservation laws in particle physics, in the standard model of particle physics, which we cannot violate. We are going to talk about those processes where we are obeying these 7 conservation laws. Then what I am telling you, that when I was introducing isotopic spin and the third component of the isotopic spin, what I told you that if we are conserving both I and I3, that is a strong interaction process. If we are not conserving I and we are conserving I3, that is an electromagnetic interaction process. And then the places where neither I nor I3 is conserved, that is a weak interaction process. And the examples that we took was, for example, pi minus p going to pi 0 plus n. As we know that pions are isotriplet and the maximum charge state will get the highest projection. Isotriplet means this is I is 1 for this, half for this, 1 for this, and half for this, because nucleons are members of iso doublets. And then the I3 is minus 1 for this, plus half for this, 0 for pi 0, and minus half for this. As you can see, both I and I3, they are conserved. And this is what we have discussed in detail while talking about the classification of interaction. Then we talked about photon scattering on proton target. We can have p and pi 0. And then here I is half here. This is half, this is 1. I3 is plus half, and 0. You see, we have a photon, and photons are quanta of electromagnetic interaction. Therefore, this is an electromagnetic interaction process. Though I and I3 both are getting conserved, but since you have a photon and photons participate only in electromagnetic interaction processes, therefore you have a process which is an electromagnetic interaction process. Similarly, we also talked about a neutrino interacting with a proton target. And in the final state, we have, for example, a muon, a proton, and a pi plus. Now you see, I is half here, and 1 here. I3 plus half, plus 1. Therefore, I3 is not being conserved, but I is getting conserved. But we know that we have a neutrino, and neutrinos participate only in weak interaction processes. Therefore, this is a weak interaction process. Now, today we are going to talk about all the weak interaction processes which are allowed by the exact conservation laws, but some of them are almost impossible to observe. Some of them have possibility 1 in billion, 1 in trillion, and so on. And that means they are extremely rare processes. Without going into the details, without going into the experiments, how we can realize that, okay, if this is the case, then this process should be observed very easily in the weak interaction case. If we have another process, by looking at some quantum numbers, is it directly possible to tell that this process will be suppressed or this process will be forbidden? This we have introduced what I call it as delta S delta Q selection rule. But formally, in this lecture, I am going to talk about this delta S delta Q selection rule in the strangeness sector, and then we will go to the charmness sector. And these are the examples which are often asked in NET, JEST, and other competitive examinations, and one should understand it very well. Therefore, first we are talking about delta S delta Q rule. Here S stands for the strangeness quantum number and Q for the charge. This rule is applied to hadrons only, as the strangeness quantum number is applied to the hadrons. Therefore, though leptons will be there, though photon, W boson, Z0 boson, etc. will be there, we will not assign any quantum number to them, whether it is charge or anything else, lepton number. Here we say that exact conservation laws are obeyed, therefore this process should be possible. Now, we also know that this is a weak interaction process, but we are not observing it. Why not? That is the main question. Then what we are talking about, when we discuss about the Cabibbo theory, I told you that there will be some Cabibbo favored decay, like we saw the example of neutron decaying into proton, electron and antineutrino, a pi minus decaying into muon and antineutrino, while we also saw the cases where a lambda is decaying into proton, electron and antineutrino, or kaon is decaying into muon and antineutrino, and so on. And I told you that at one place you will have a vortex factor of cos theta c, another place we have vortex factor of sin theta c. Vortex factor of cos theta c will be there if the transition will in the quark sector will be in the same generation, U to D or D to U, or C to S or S to C. But if the transition is from one generation to another generation, you will have sin theta c, and those will be the Cabibbo suppressed processes. Now, allowed plus Cabibbo suppressed, when the net change in strangeness delta S and net change in the charge of the hadrons are equal. That means delta S is equal to delta Q is equal to plus 1, or delta S is equal to delta Q is equal to minus 1. This will be Cabibbo suppressed. While when the net change in strangeness is 0, that will be Cabibbo favored, as we saw N decaying into P plus E minus nu E bar, or pi minus decaying into nu mu bar. As you can see, there is no strange particle involved in this. Therefore, change in strangeness quantum number is 0. Forbiddance are the cases where delta S is equal to minus delta Q, or simply we can say that delta S is equal to minus delta Q is equal to plus 1, or delta S is equal to minus delta Q is minus 1. These will be forbidden processes. Then we also discussed the cases where delta S is greater than or equal to 2. These will be also forbidden processes. We discussed the idea of W propagators, that if you have the conversion of two quarks to different flavors of quarks, you involve two W bosons, and because of the propagators, we have discussed it in one class, you will have a strong suppression, and that is why those processes are forbidden processes. And we took the examples of the different reactions. We also saw the example of sigma minus decaying into N plus electron plus antineutrino, has been observed in nature, that is an allowed process, though Cabibbo suppressed, but sigma plus decaying into n plus E plus nu E. This is a forbidden process. We saw that because of this delta S is equal to delta Q, that was equal to minus Q. This is not an allowed process, but the reason for that, when we looked at the core configuration of these sigma plus baryon and neutrons, we saw that actually it required conversion of two flavors of quarks into another flavor, and that means two W boson propagators. Now, the important point is that what I am telling you, that if you have A plus B going to say give you alpha plus beta plus gamma plus delta, and if this gamma and delta are some lepton or anti-lepton, or lepton or an anti-neutrino, L stands for E mu tau. Any electron type, electron, positron, electron, anti-neutrino, and whatever you talk about. Then if you have some other particles here, other than hadrons, you won't talk about assigning quantum number to them. Mind it, the important point is when I am talking about neutron decaying into proton plus electron plus anti-neutrino, and I tell you that this is an observed process. This will be only possible when charge will be conserved, because that belongs to the category of exact conservation laws. This is only possible when you consider the charge of the electron. But for the delta S delta Q rule, we won't talk about these leptons. We understand that without the conservation of charge or lepton number or baryon number or other things, the process will not be possible. But this delta S delta Q rule will be assigned to only hadrons, that means baryons and mesons. And that means if, for example, this is a strange particle, this may have a strangeness quantum number +1 or -1 or +2 or -2. If this is a non-strange particle, this will be 0. If this is a strange particle, this can be +1 or -1. And if this is also a strange particle, for example, then it can be +1 or -1. For example, if I say that pi minus p is giving me lambda 0 plus k0. You see, we have two strange particles. But what is the point? Strangeness quantum number for lambda 0 is -1. For k0, it is +1. Therefore, if you look at the isospin, this is 1, this is half, this is isosinglet, this is a member of k plus, which is a doublet. Therefore, this is half. I3 -1 plus half, this is 0. And remember, k plus and k0 were placed in a doublet. This is -half. Therefore, the important point is you are conserving I3, you are conserving I. Therefore, this will be a strong interaction process. And in fact, this is associated particle production which has been observed in the experiments. Particles with opposite strangeness. Lambda 0, k0. Similarly, you can think of sigma 0. For example, if I take pi minus plus p, sigma 0 plus k0, then I will be, and I3, this is 1, this is half, this is 1, this is half, everything is fine. I3 -1 plus half, 0 minus half. You can see that we are conserving I as well as we are conserving I3, but this is again a strong interaction process. Now you see, the important point is that if you look at the total charges, therefore net charge, if you talk about this, if we are unable to conserve the charge of the particles, then this process should not be observed. You can see that pi minus and p charges, some of the charges are 0, and here on the right hand side is 0, and strangeness on the left hand side 0, and strangeness on the right hand side -1 and +1, that will give us 0. Therefore, these are additive quantum numbers, and here we are getting 0, here we are getting 0. Strangeness is conserved in a strong interaction process, and charge has to be conserved, without that is given by nature. Therefore, here all hadrons are the particles involved in the interactions. Here, that means if we are talking about delta S delta Q rule, that exists because delta S, the net change in strangeness, and is equal to the net change in charge, because the net change in charge is 0. But the important point is, we are going to talk about the particles where we have delta S, for example, is 0 and delta Q plus minus 1. For example, if I talk about neutron decaying into proton plus electron plus antineutrino, then strangeness 0, 0, charge 0 plus 1. Therefore, delta Q is plus 1 while delta S is equal to 0. Remember what I had told you, that if delta S is 0, then that will be a Cabibot favored process. If delta S is 0, that will be a Cabibot favored process. Whereas if I talk about lambda 0 decaying into proton plus electron plus antineutrino, and S and Q I talk about, for lambda is minus 1, for proton it is 0, charge for lambda is 0, for this is plus 1. Therefore, you see delta S is plus 1, delta Q final minus initial, it is plus 1, final minus initial, and that means if delta S is equal to delta Q is equal to plus 1, this will be Cabibot suppressed process. Similarly, if I talk about sigma minus decaying into n plus E minus plus nu E bar, you notice strangeness quantum number minus 1, charge minus 1, here this is 0, this is 0. Therefore, delta S final minus initial, delta Q final minus initial, delta S delta Q is plus 1. This will be again a Cabibot suppressed process. If you recall the quark configuration of lambda 0, this is UDS, this is UDU. Therefore, S is changing to U, and recall S is changing to U. The transformation from one generation to another, that will have sine theta c, and that will be a Cabibot suppressed process. Therefore, these processes will be Cabibot suppressed processes, while this process will be Cabibot favored process, because you remember neutron is UDD and this is UDU. Therefore, conversion of D to U in the same generation, that will contain at the vertex a factor of cosine theta c. So, this is what we are going to talk about. And then we also talked about sigma plus decaying into neutron plus E plus nu E. Then here strangeness is minus 1, this is 0, this charge is plus 1 and this is 0. Therefore, delta S is plus 1 while delta Q is minus 1. Therefore, delta S is minus delta Q is plus 1, and this will be a forbidden process. And this I told you in the class, that this sigma plus means strangeness is minus 1 and this is UDD. You needed two quarks to change their flavors, and that will be forbidden processes. Therefore, without looking at the quark level, directly by applying these rules, you can say that this process will be a forbidden process. Similarly, you can take example of omega minus decaying into n plus pi minus, omega minus decaying into sigma 0 pi minus, omega minus decaying into cascade 0 pi minus, or cascade 0 decaying into proton plus pi minus, cascade 0 decaying into sigma 0 plus pi 0, cascade 0 decaying into sigma plus pi minus, or sigma plus sigma minus. We have dealt with the cases. Therefore, what you see, that strangeness quantum number is minus 3, this is 0. So, delta S change is plus 3. and that will be a forbidden process because delta S cannot be greater than or equal to 2. And this again minus 3 minus 1, this is 2. While here straightness is minus 3, this is minus 2, 0, delta S is plus 1. And Q minus 1, 0, minus 1. Therefore, the net charge changes. Delta Q is 0, delta S is equal to plus 1. Therefore, this should be an observed process, but this is containing a delta S is equal to plus 1, and that will be a suppressed process. Therefore, here through the quark diagrams, I am showing you that how we are talking about a neutron getting converted into a proton by a d quark changing to u quark by emitting a W minus, and that W minus is giving rise to E minus and nu E bar. And as you can see that this is a Cabibbo favored process, while if we consider lambda decaying into proton plus electron plus antineutrino, you can see that S is getting converted into U, mixing between the two generation of quarks, and here that should contain a factor of sine theta c, and therefore this should be a Cabibbo suppressed process. Similarly, we talked about sigma minus decay, then we talked about sigma plus decay, and we have here lambda 0 plus E plus nu E. You see straightness is minus 1, here straightness is minus 1, therefore net change in straightness is 0, Q is plus 1 and here Q is 0, therefore net change in charge is minus 1. But if straightness is 0, change in straightness is 0, that should be a Cabibbo favored process. And if you recall, sigma plus is UUS while lambda is UDS. Therefore, we are talking about a transition from U to D in the same generation, and that means that should contain at the vortex a factor of cosine theta c, and that should be a Cabibbo favored process. Similarly, if you talk about a sigma minus decaying into lambda plus E minus plus nu E bar, straightness is minus 1, here it is minus 1, charge is minus 1, and here charge is 0. Therefore, straightness is 0 and delta Q is plus 1. But at the same time, I told you a process where sigma minus decaying into N plus E minus plus nu E bar. This will involve straightness minus 1, charge minus 1, straightness minus 1 and charge minus 1. This is straightness 0 and this is straightness 0. Therefore, this is delta S plus 1, delta Q plus 1. This is Cabibbo suppressed process. While at the same time, sigma plus is allowing this, but sigma plus decaying into N plus E plus nu E. This involves minus 1 and 0, and charge is plus 1 and 0. This is a forbidden process. Then sigma 0 decaying into at rest, sigma 0 decaying at rest is decaying into sigma plus E minus plus nu E bar. This is, though you will see that delta S is 0 and delta Q is plus 1, but the catch is the mass of sigma 0 is smaller than the mass of sigma plus, and therefore a particle of lower energy cannot decay into a particle of higher energy, that you will violate the energy conservation law. Therefore, this you will never observe in nature. Then sigma 0 decaying into P plus E minus nu E bar. You know that sigma 0 is UDS and proton is UDU. Therefore, straightness S quark is changing to U quark, mixing between the two generations, and that will be a Cabibbo suppressed process. Therefore, just by assigning Q and S, directly you can say that if delta Q, delta S is plus 1 or minus 1, that should be Cabibbo suppressed process. If delta S is 0, that will be Cabibbo favored process, and if delta S is greater than or equal to 2, then that will be a forbidden process, as well as if delta S is delta Q minus delta Q is plus minus 1, that will be a forbidden process. Then sigma 0 decaying into lambda plus gamma, again a photon is involved, and you see delta S is 0, delta Q is 0 because in electromagnetic interaction, strangeness is conserved. Therefore, we have a process where strangeness is conserved and charge is conserved. If you look at the isotopic spin, this is 1, this is 0, I3, 0, 0. Remember, I told you while in the beginning of the class that I is not conserved in electromagnetic interaction, but I3 is conserved in electromagnetic interaction. Therefore, sigma 0 decaying into lambda plus gamma. But without going into these details, directly you can, if you look at a process where you have a photon, electromagnetic process. If you look at a process where you have a neutrino, then that is a weak interaction process. Therefore, these things we have to keep in mind. Similarly, we have cascade 0 decaying into sigma plus E minus nu E bar. You can say that strangeness is minus 2. Here strangeness is minus 1. Therefore, the net change in strangeness is plus 1 and net change in charge is plus 1. Therefore, this will be a Cabibbo suppressed process. Similarly, you can consider another decay like of cascade minus decaying into sigma 0 E minus and nu E bar. You can say that delta S is plus 1 and delta Q is plus 1. That will be a Cabibbo suppressed process. Therefore, we have a Cabibbo favored, Cabibbo suppressed as well as forbidden processes which we have to consider while writing the transition amplitude. Then I took the example of sigma plus decaying into N plus E plus nu E as delta S is not equal to delta Q. That delta S is of minus of delta Q. That will be a forbidden process. Then we took the example of hadronic decay modes, and this we will start in the next class. We will start the discussion of the processes or the decays where you have all the hadrons in the final state, and we will see that what are their branching ratios and how do we understand these processes and how then we apply Charmness quantum number to understand that if the charm quark is involved or anti-charm quark is involved, whether that will be a favored, suppressed or a forbidden process. Let us stop here. Thank you very much.